Hey everyone, and welcome to The Explainer. Let's dive right in and unpack the ancient number theory that is literally locking up our modern digital world. For those of you who already know your way around basic encryption, you're well aware that the math gets incredibly complex, incredibly fast. But today, we're going to look under the hood and completely demystify the foundation of it all. So I want to start off by asking you to consider a pretty stunning contrast. How exactly do mathematical concepts formulated in antiquity end up guarding your most sensitive digital data today? I mean, every single time you send a secure text or check your bank balance or buy something online, you are relying on principles that were discovered millennia before computers even existed. We're going to explore exactly how that happens. We're going on a historical journey together, tracing ideas from ancient Greek number theory all the way to the complex cryptographic algorithms securing today's internet. Because our modern public key encryption, it isn't some recent invention cooked up in a Silicon Valley lab. It's actually the culmination of centuries of mathematical breakthroughs. From Euclid in antiquity to Fermat and Euler in the 17th and 18th centuries, right up to the Miller-Rabin primality test in the 1970s. Every single era built the necessary tools for the digital security we use today. Here's our syllabus for today's Explainer. We're going to cover the roots of digital security, walk through the Euclidean algorithm step by step, make modular arithmetic simple, talk about primes, explore Fermat and Euler's theorems, and then conclude with a quick number theory exam review. Okay, Section 1, the roots of digital security. Let's start with the fundamental bedrock of all cryptography, which is divisibility. The division algorithm basically shows how any integer, which we'll call a, is broken down into a quotient q and a remainder r when it's divided by n. So a equals q times n plus r. Essentially, any number falls just past a multiple, leaving that vital remainder. And in cryptography, it's actually that remainder, which is often called a residue, that we are the most interested in. Moving on to Section 2, the Euclidean algorithm step by step. Now that we've got the division algorithm down, let's see how Euclid used it to find the greatest common divisor. It's kind of like a cascading waterfall of numbers. The remainders form a descending series, dropping down until the remainder is exactly 0. Let's look at the numbers 710 and 310. We divide 710 by 310 and we get a remainder of 90. Now we shift the divisor and remainder over, divide 310 by 90 and we get a remainder of 40. We just keep cascading until we divide 40 by 10, leaving a remainder of 0. That last non-zero remainder, which is 10, is our greatest common divisor. For any beginners out there, here's the clear tutorial-style procedure you need to follow every single time you run the Euclidean algorithm. You just divide, find the remainder, shift your numbers to the left, and repeat. You stop the absolute second your remainder hits 0. It's a remarkably elegant loop that guarantees you are going to find the largest integer that divides your two starting numbers perfectly, without leaving a remainder. Now, the really cool part is that this algorithm scales incredibly well. For instance, finding that the GCD of the massive 10-digit integers 1160718, and 316258250 is exactly 1078, it takes just a handful of steps. Similarly, if we ran it on another huge pair, like 4187552 and 2133024, it aggressively collapses them down to a GCD of 32 in mere seconds. This efficiency is exactly why it's actively used inside your computer systems today. Section 3, modular arithmetic made simple. So, to simplify complex integer operations, we use modular arithmetic. This is the operating environment where nearly all modern cryptographic math takes place. Just think of the modulus like a clock. Once you pass 12, you loop back around to 1, which is really just another way of saying we only care about the remainder. If it's 10 o'clock and you add 4 hours, well, it's 2 o'clock, right? That's 14 modulo 12. Modular arithmetic basically confines our calculations to a fixed, finite set of numbers, preventing our cryptographic equations from expanding into infinity and keeping them actually computable. Here are the core rules of congruences for your quick reference. These rules dictate exactly how these wrapped, looped numbers interact. When we say A is congruent to B modulo n, all we mean is they have the exact same remainder. And because these congruences are commutative and transitive, they behave exactly like standard equal signs. This is a total superpower. It allows us to perform massive calculations using much smaller equivalent remainders. All right, Section 4, primes and digital security. Let's talk about the absolute VIPs of digital security, prime numbers. While composite numbers can be shattered into smaller pieces, primes are the unbreakable atoms of our cryptographic universe. Every single composite number is just a multiplication of primes. The fundamental theorem of arithmetic guarantees this. In digital security, we actually exploit this as a one-way street. Multiplying two massive prime numbers is incredibly easy for a computer. But taking the resulting composite number and trying to shatter it back into its original primes, that is practically impossible. But here's the catch. We need massive, unpredictable primes for public key cryptography to work securely. So how do we find them? Algorithms like Miller-Rabin are absolutely essential here. We obviously can't just try dividing a massive 200-digit number by every single integer to see if it's prime. That would take longer than the age of the universe. Instead, we use the Miller-Rabin test, which perfectly leverages modular arithmetic to test for primality with unbelievable speed. Now, it might shock you a bit that our modern security relies on a probability test, but doing it enough times guarantees security margins that are practically unbreakable. The test basically looks at the properties of remainders. Each time a number passes the test, the odds of it actually being composite drop by a factor of 4. If you run the test just 10 times, the chance of a false positive is less than 1 in a million. Run it 50 times, and it is a mathematical certainty for all practical intents and purposes.
Section 5. Fermat and Euler's theorems.
This right here is where those centuries-old ideas truly come alive to make massive computations possible. Fermat's theorem states that if p is prime, a to the power of p minus 1 is congruent to 1 modulo p. Guys, this is a massive shortcut. For example, if you need to calculate 5 to the 6th power modulo 7, you don't need to do any heavy lifting. Because 7 is prime, Fermat's theorem guarantees the answer is simply 1. Boom. You can instantly reduce insanely large exponents down to perfectly manageable sizes.
And finally, Section 6, Number Theory Exam Review. Let's do a rapid-fire exam review to solidify these abstract concepts. First up, remember the GCD, which we easily extracted using that Euclidean algorithm we walked through earlier? Understanding how to quickly find the GCD and recognizing when two numbers have a GCD of exactly 1, which means they are relatively prime, is literally step 1 in generating your encryption keys.
Second is Euler's totient function, which is vital because it determines the number of relatively prime integers. If you have a composite number n made of two primes, p and q, the totient is simply p minus 1 times q minus 1. So for example, if your primes are 3 and 5, your totient is just 2 times 4, which is 8. This very specific mathematical trick is the direct, foundational bedrock of the RSA encryption that secures the modern internet. So what's the ultimate takeaway here? It's that abstract number theory isn't just some dry academic exercise. It actively protects every single piece of data you transmit online. Primes provide the lock, modular arithmetic provides the finite space to calculate the key, and algorithms from brilliant mathematical minds make it all run in a fraction of a second on your smartphone. I want to leave you with this final thought. As our technology continues to advance at lightning speed, we really have to wonder if these ancient mathematical fortresses are going to stand forever or if they'll eventually need an upgrade. With the dawn of quantum computing right on the horizon, the way we calculate these unbreakable primes might actually face an existential threat. But until then, you can thank Euclid, Fermat, and Euler for keeping your digital life secure. Thanks for joining me on this explainer. Keep exploring, and I'll catch you in the next one.